Imagine holding a window to a world that vanished 70 million years ago. That is exactly what happened when scientists in southern China looked inside a fossilized egg. They found something incredible. Inside was the embryo of a dinosaur, perfectly preserved. This tiny creature, nicknamed Baby Yingliang, was curled up, ready to hatch. It was an oviraptorosaur, a type of beaked, feathered dinosaur. This discovery was not just another old bone. It was a complete baby dinosaur, frozen in time just moments before it would have entered the world. It gives us a rare glimpse into the very beginning of a dinosaur's life, a moment that has been hidden from us for millions of years. Fossils are our only direct connection to the dinosaurs. They are the storybooks of ancient life. Each bone, each footprint, and each tooth tells a chapter of that story. From a single fossilized tooth, we can learn what a dinosaur ate. Was it a sharp tooth for tearing meat, or a flat one for grinding plants? The bones themselves tell us even more. By studying the size and shape of leg bones, we can figure out how large a dinosaur grew and how fast it could run. Footprints preserved in ancient mud show us how they walked, whether they moved in herds, and how they interacted with their environment. These clues, pieced together, help us build a picture of these magnificent animals. The discovery of baby Yingliang is so exciting because embryos are incredibly rare. The delicate bones of a baby dinosaur are usually crushed or scattered before they can become fossils. Finding one so complete is like winning the lottery for a paleontologist. This little dinosaur was preserved in a unique posture. Its head was tucked under its arm, its back was curled, and its feet were on either side of its head. This position, known as tucking, was thought to be unique to modern birds just before they hatch. Finding it in a dinosaur embryo is a stunning revelation that deepens the connection between dinosaurs and the birds we see today. This single fossil has opened up a whole new area of research. It helps us answer questions we have had for a long time. How did dinosaurs develop inside their eggs? Did they move around? Did they prepare for hatching in the same way as their modern relatives? Before baby Yingliang, we could only guess. Now, we have solid evidence. This embryo is not just a fossil. It is a time capsule. It carries biological information that has been locked away for eons. It provides a direct link to the developmental biology of these extinct giants, allowing us to understand their journey from a tiny embryo to a fully grown animal. To study baby Yingliang, scientists needed to see inside the egg without breaking it. Destroying such a rare fossil would be a tragedy. This is where modern technology comes to the rescue. The team used a powerful technique called computed tomography, or CT scanning. A CT scanner takes thousands of X-ray images from different angles. A computer then puts these images together to create a detailed, three-dimensional model of whatever is inside. This allowed the scientists to digitally remove the rock and the eggshell, revealing the tiny skeleton of the embryo in stunning detail. They could see every single bone exactly as it was positioned 70 million years ago. This non-destructive method is a game-changer for paleontology. In the past, scientists had to carefully chip away at the rocks surrounding a fossil, a slow and risky process. One wrong move could shatter a delicate bone. With CT scanning, we can explore the internal structures of fossils with incredible precision. We can see inside skulls to study the shape of the brain. We can look at the inner canals of the ear to understand a dinosaur's hearing and balance. For baby Yingliang, it meant we could measure its bones, study its posture, and compare it to other animals without ever touching the fossil itself. The analysis of baby Yingliang went beyond just looking at its bones. Scientists can also study the chemistry of the fossil and the rock around it. These chemical signatures can tell us about the environment the dinosaur lived in. They can give clues about the temperature and conditions at the time the egg was laid. While the embryo itself is now stone, traces of the original biological material can sometimes remain. Future studies on this fossil might look for microscopic remnants of proteins or other organic molecules. Such discoveries would be revolutionary, giving us an even deeper understanding of dinosaur biology at a molecular level. From these detailed scans and studies, a story began to emerge. The scientists learned that oviraptorosaurs like baby Yingliang likely developed faster than many other types of dinosaurs. Its advanced stage of development, combined with its bird-like tucking posture, suggests it would have been quite active and capable shortly after hatching. This is similar to many modern ground-nesting birds, whose chicks are born ready to run. This little dinosaur was not a helpless baby. It was preparing to burst out of its shell and begin its life in a world filled with giants, a world we are only now beginning to truly understand through these amazing windows to the past. One of the most mind-blowing discoveries from baby Yingliang is its posture. The way its head was tucked beneath its right wing is a behavior we see in bird embryos today. This tucking is a crucial step for a successful hatch. It helps the chick stabilize its head so it can use its beak to break through the eggshell. Finding this exact same behavior in a non-avian dinosaur embryo is a powerful piece of evidence. It shows that this complex pre-hatching behavior did not evolve in birds. It originated much earlier, within their dinosaur ancestors. This fossil proves that the link between dinosaurs and birds is not just skeletal, it is also behavioral. This connection is part of a growing mountain of evidence. For decades, paleontologists have been finding fossils that blur the line between dinosaurs and birds. We have discovered dinosaurs with feathers, wishbones, and hollow bones, all features we once thought were exclusive to birds. Dinosaurs like Velociraptor, made famous by movies, were covered in feathers. Oviraptorosaurs, the family baby Yingliang belongs to, were especially bird-like. Some were even found sitting on nests of eggs, brooding them just like a modern chicken. These discoveries have completely changed our view of dinosaurs. They were not just scaly monsters, they were active, complex, and feathered animals. The feathers themselves tell a fascinating story of evolution. The first feathers on dinosaurs were probably not for flight. They were likely simple filaments, more like hair, used for insulation to keep warm. Over millions of years, these simple structures evolved into the complex, branching feathers we see today. Some dinosaurs may have used them for display, to attract mates or intimidate rivals, using bright colors and patterns. Only later did some small, lightweight dinosaurs adapt these feathers for gliding and eventually for powered flight. Baby Yingliang, as an oviraptorosaur, would have almost certainly been covered in at least simple downy feathers. So when you look at a pigeon in the park or a chicken in a farmyard, you are looking at a modern-day dinosaur. Birds are not just related to dinosaurs, they are dinosaurs. They are the one branch of the dinosaur family tree that survived the asteroid impact 66 million years ago. Baby Yingliang helps us understand the origin of birds more clearly than ever before. It shows that many of the traits we consider bird-like were already present in their dinosaur ancestors. This tiny embryo locked in stone is a direct message from the past, reminding us that the legacy of the dinosaurs is all around us, flying in our skies. What would have happened if baby Yingliang had hatched? If a mudslide had not buried its nest, this tiny creature would have broken free from its shell. As an oviraptorosaur, it would have entered a world dominated by colossal dinosaurs. It would have likely stayed close to its parents for protection. We know from other fossils that some oviraptorosaurs were carrying parents. The baby would have grown quickly, feasting on small animals, eggs, and possibly plants. It would have navigated a dangerous landscape, avoiding predators like tyrannosaurs. It would have grown its own coat of feathers, perhaps developing bright colors for display as it reached adulthood and looked for a mate of its own. This single embryo brings the world of dinosaurs to life in a way that skeletons in a museum cannot. It also sparks our imagination and makes us ask big questions. The idea of bringing dinosaurs back, popularized by books and movies, is a fantasy for now. The biggest hurdle is the lack of dinosaur DNA. DNA is a fragile molecule that breaks down over time. Scientists have not found any usable DNA from dinosaur fossils, which are simply too old. Even if we found a fragment, we would have no complete blueprint to work from. Baby Yingliang, being a fossil, contains no DNA. It is a perfect stone copy of the original animal. However, the close connection between dinosaurs and birds offers another, more plausible path. Since birds are living dinosaurs, their DNA holds the genetic echoes of their ancestors. Scientists are already studying how to reverse evolve a chicken by switching certain genes on or off. The goal is not to create a Tyrannosaurus rex, but to understand the genetic changes that turn dinosaurs into birds. Could we one day hatch a chicken with teeth, or a longer, more dinosaur-like tail? It is a fascinating and controversial area of research. Baby Yingliang gives us a better target, showing us exactly what a late-stage dinosaur embryo looked like. Ultimately, the discovery of baby Yingliang is a triumph for science and a gift to our curiosity. It reinforces the deep evolutionary bond between dinosaurs and birds. It showcases how technology can unlock secrets hidden for millions of years. It reminds us that there are still incredible discoveries waiting to be made, buried beneath our feet. This tiny dinosaur, which never took a single breath, has breathed new life into our understanding of the ancient world. It ensures that the story of the dinosaurs, a story of evolution, extinction, and survival, will continue to captivate and inspire us for generations to come.